You are losing money every single day because of a technology that was killed before you were even born. Not wasted in some obvious way, not on subscriptions or bad purchases, but silently, systematically, built into the way your world works. And the worst part is this: the solution existed decades ago. It worked, it was tested, it was ready, and then we abandoned it. In this episode, I'm going to walk you through 7 turning points that explain how a technology buried in the 1960s came back and is now worth $3.3 billion. Point 3 is where we made the biggest mistake. Point 5 is the one no one likes to talk about. And point 7 will change how you look at modern technology forever. At the end, I'll give you a simple test, something you can use immediately to spot when we're about to repeat the same mistake again. Don't scroll. Let this land. In 1961, in a quiet research lab in New Jersey, engineers at Bell Labs were working on something strange. It didn't look like the future. It wasn't fast. It wasn't flashy. It didn't promise to change the world overnight. But it solved a problem so cleanly that, if we had followed that path, the entire trajectory of modern electronics could have been different. The idea was simple. Instead of forcing electricity through wires the way we always had, they asked a different question. What if we used sound instead? Not sound you can hear, sound moving through solid material, controlled, precise, predictable. They built tiny structures that could take an electrical signal, convert it into a mechanical wave, send it across a surface, and turn it back into electricity again. It sounds abstract, but what it meant in practice was this. You could filter, delay, and shape signals with incredible precision, using physics instead of brute force electronics. At the time, it was called acoustic wave technology. And it worked. Now pause for a second, because this is where the story usually gets told wrong. Most people assume that when a technology disappears, it's because it failed. It didn't work. It was too expensive. It was impractical. That's not what happened here. I know what you're thinking. If it was so good, why didn't it take over? Here's why. Because something else came along at exactly the wrong time. In the late 1960s and early 1970s, silicon integrated circuits started to explode. Transistors were shrinking. Chips were getting cheaper. Digital logic was becoming the dominant language of engineering. And compared to that, acoustic systems looked old. They required precision materials, careful design, physical understanding. While silicon promised something seductive, scale, millions of identical units, manufactured fast, improved every year. So companies made a choice, not based purely on performance, but on momentum. They followed silicon. And quietly, almost without anyone noticing, acoustic wave technology was pushed to the side. Not killed overnight, but deprioritized, underfunded, forgotten. This is the first turning point, and emotionally it matters more than it seems. Because this wasn't just about engineering, it was about how decisions get made. Imagine a young engineer in 1972. He has 2 paths. One leads to silicon, fast growth, funding, excitement, career stability. The other leads to acoustic systems, slower, more complex, uncertain. Which one does he choose? Multiply that decision by thousands of people across labs, companies, universities. That's how a technology disappears, not because it's bad, but because it's inconvenient at the wrong moment. But here's where it gets uncomfortable, because the problem acoustic systems solved didn't go away. It just got worse. Fast forward to today. Your phone, your Wi-Fi router, your car, your headphones, they all rely on clean signals. Signals that must be separated, filtered, controlled. If they overlap, everything breaks. Calls drop, connections lag, devices interfere with each other. Now here's the number most people don't realize. A modern smartphone handles signals across dozens of frequency bands. Each one needs to be isolated. Each one needs to be clean. And each one is fighting for space. So what did we do? Did we solve it with pure digital silicon? No, we couldn't, because at a certain level, digital processing is too slow, too power hungry, too messy. So we went back to physics, back to waves, back to the idea that Bell Labs explored in 1961. But don't jump ahead yet, because the second turning point explains why this comeback took decades. In 1965, two researchers, Robert White and Fred Voltmer, introduced something called the interdigital transducer. It sounds complicated. It isn't. Imagine two combs, their teeth interlocked. Now place them on a flat surface. When you apply an electrical signal, that pattern launches a tiny wave across the surface. That wave carries information, and depending on how you design those teeth, you can decide exactly which signals pass and which don't. This became known as the surface acoustic wave filter, and for a brief moment it looked like acoustic technology might actually win. Companies started experimenting. Military systems adopted it. Television manufacturers used it to clean up signals. Engineers saw the potential, but then reality hit again. I know what you might be thinking. Okay, so it was useful. Why didn't it dominate? Here's why. Because it still couldn't compete with the sheer speed of silicon's progress. Moore's law was accelerating everything. Every year chips got better, cheaper, more powerful. And once again, the industry made the same decision. Follow the momentum. This is the second turning point, and it's where a pattern starts to emerge. We don't always choose the best solution. We choose the one that scales fastest right now, even if it creates problems later. Stop here for a second, because the next part explains something most people never notice. When a technology is abandoned, it doesn't disappear completely. It goes underground, into niche applications, into specialized industries, into places where performance matters more than hype. Through the 1970s and 80s, acoustic wave devices didn't vanish. They moved into radar systems, military communications, early signal processing equipment, places where failure wasn't an option, where interference meant real consequences, where precision mattered more than cost. Think about that. While the consumer world rushed forward with silicon, quietly, in the background, engineers kept refining acoustic systems, making them better, smaller, more reliable. No headlines, no hype, just slow, steady improvement. This is the third turning point, and it's the one that should make you uncomfortable, because it shows how often the obsolete technology isn't actually obsolete, it's just waiting. Imagine a retired couple living outside a city. They have an old piece of equipment in the garage, something they used decades ago. Everyone else moved on, upgraded, forgot about it. But one day a problem appears, and suddenly that old tool is exactly what's needed. That's what happened here. Because by the time we reached the 2000s, something changed. The world became wireless. Not partially, completely. Phones, internet, GPS, Bluetooth, everything. And suddenly the old problem came back, amplified. Too many signals, too little space, too much interference. And this time, silicon alone couldn't save us. By the early 2000s, something broke. Not visibly, not all at once, but if you were paying attention, you could feel it. Calls dropping in crowded cities, Wi-Fi slowing to a crawl in apartment buildings, devices interfering with each other in ways no one expected. The system we built, fast, digital, scalable, had a blind spot. It was never designed for this much noise. Let's make this real. Imagine a man in his mid-40s living in a city apartment. He wakes up, checks his phone. His Wi-Fi struggles because 20 other routers are on the same channel. He takes a call. It cuts out when he enters an elevator. He connects Bluetooth headphones. They glitch near traffic lights. Nothing catastrophic, just friction, small losses, every day. Here's the number. In dense urban areas, a single smartphone can be exposed to signals across 50 to 90 active frequency channels at any given moment. That's not just crowded, that's chaos. And here's the uncomfortable truth. We built a world where everything talks at once, but we didn't build enough ways to keep those conversations separate. This is where the forgotten technology comes back, quietly, without headlines. Engineers started asking a question that sounded very familiar. What if we stop trying to fix everything with software and go back to physics? And suddenly, the old ideas made sense again. Acoustic wave filters, surface waves, bulk waves, the same principles explored decades earlier. But this time, the context was different. Now we needed them. This is the fourth turning point, and it's where history stops being a story and becomes a cycle. I know what you might be thinking. Why didn't we just improve digital processing instead? Here's why that doesn't work. Digital systems handle signals after they arrive, but interference happens before that. If the signal is already corrupted, no amount of software can fully fix it. It's like trying to understand someone speaking in a crowded room after their voice has already been drowned out. You don't need better interpretation, you need silence around the signal. And that's exactly what acoustic filters provide. They act as gatekeepers, letting the right frequencies pass, blocking everything else, before the chaos even begins. Pause here, because this is the moment everything clicks. We didn't just rediscover an old technology. We realized we had never replaced it. We had only postponed the need for it. Now let's go deeper, because the comeback didn't happen all at once. In the early 2000s, companies began integrating surface acoustic wave filters into mobile devices. At first, just a few, then more, then many more. By the time fourth-generation networks became standard, a single smartphone could contain 50 to 70 filters. By fifth generation, that number pushed toward 100. Each one doing a very specific job, each one solving a problem silicon alone could not. Think about that. Inside the phone you carry every day, there are dozens of tiny components based on a technology we nearly abandoned. Emotionally, this is where the story hits, because it means this: the world you rely on every day is built on something we almost lost. And here's where the number comes in. By the mid-2020s, the market for these acoustic filter technologies reached roughly $3.3 billion. Not trillion, not hundreds of billions, just a few billion. Which makes it even more interesting, because it's small enough to ignore, but critical enough that without it, nothing works. This is the fifth turning point, and it's the one most people never see. The most important technologies are often not the biggest. They're the ones that everything else depends on. Think of it like this. A retired mechanic keeps a small, obscure tool in his garage. Cheap, forgotten, outdated. But one day, a modern engine fails, and none of the expensive new tools can fix it, except that one. That's what acoustic filters became. But here's the part that should make you stop, because we're about to repeat the same mistake again. The world is moving toward even denser systems. More devices, more signals, more overlap, smart homes, smart cities, autonomous vehicles, each one adding another layer of complexity, each one increasing the chance of interference. And once again, the industry is tempted by the same pattern. Push forward with what scales fastest, ignore what works quietly. I know what you're thinking. Technology is more advanced now. We won't make the same mistake. Here's why that's not true. Because the mistake wasn't technical. It was human. We follow momentum. We chase trends. We prioritize what grows fastest, not what holds everything together. And that brings us to something you can actually use. Here's your free tool. Simple, practical, immediate. Whenever you see a new technology, a device, a system, a network, ask, what is separating the signals? Not how fast it is, not how smart it is, not how many features it has, just that one question. Because if you can't find the answer, it means the system is fragile. Try this today. Look at your router, your phone, your car. Ask yourself, where are the gatekeepers? What is preventing interference? You'll start to see something most people never notice. But this is only part of the system. Because knowing the question is powerful, but knowing how to apply it across different technologies, industries, and future trends, that's what changes how you think. And that's where everything comes together. I've taken this exact pattern, forgotten technologies, hidden dependencies, and the mistakes we repeat, and turned it into a structured way to analyze modern tech. So instead of reacting to hype, you can predict what actually matters. It includes how to spot abandoned technologies before they come back, how to identify hidden infrastructure inside everyday devices, how to avoid investing time and money into fragile systems. Everything together is here. Link in the description. But stay, because the next part is the most important. In the final part, we're going to push this forward, not into the past, but into the future. And I'll show you exactly where the next abandoned technology is hiding right now, and why the people building it already know something the rest of the world doesn't. We've been looking backward. Now let's do something more dangerous. Let's look forward. Because the real story is not that we killed the technology and brought it back. The real story is that we are doing it again, right now. Take a step back and look at the direction everything is moving. More devices, more signals, more layers. Not 10 connections, hundreds. Not one network, many overlapping networks. Your phone is already handling dozens of channels. Your home has Wi-Fi, Bluetooth, maybe smart devices. Your car is becoming a network on wheels. Your city is slowly turning into a grid of sensors. And every one of these systems depends on the same fragile condition. Signals must stay separate. Break that and everything starts to degrade. Slowly at first, then all at once. Let me show you what that actually looks like. Imagine a couple in their 50s. They've just installed a full smart home system. Lights, locks, cameras, thermostat, everything connected. At first, it feels perfect. Lights respond instantly. Doors lock automatically. Temperature adjusts itself. Then small things start happening. The camera lags when someone streams video. The lock responds slower at night. The thermostat disconnects once a week. Nothing catastrophic, but something feels unreliable. What they don't see is this. All of those devices are competing for space, for clarity, for signal. And if the system wasn't designed with strong gatekeepers, with proper filtering, separation, planning, it starts to break under its own weight. This is the same problem, just scaled up. Now take that idea and expand it. Self-driving cars communicating in real time, hospitals running wireless monitoring systems, factories coordinating machines without cables. Each one depends on clean communication, not just fast, clean. Here's where it gets serious. In 2022, studies from multiple engineering groups showed that dense wireless environments can experience signal collision rates above 30% under poor design conditions. That means nearly 1 in 3 transmissions can interfere with another. Translate that into real life. A delayed message between cars, a missed update in a medical system, a failed command in an automated process. Not dramatic on its own, but stacked together, it becomes risk. This is why the filter story matters, because it's not about phones, it's about systems that either hold or collapse. Stop here. Don't rush this part. The difference between a stable future and a chaotic one is not speed, it's separation. And this is where the pattern becomes clear. We always do the same thing. We chase growth. We build fast. We scale aggressively. And only later do we realize we forgot the invisible layer that keeps everything working. I know what you might be thinking. Okay, but engineers already know this. It's handled. Here's why that's not enough. Because the problem isn't awareness, it's priority. When budgets tighten, what gets cut first? Invisible systems, infrastructure, things users don't see. Exactly like acoustic filters in the 1960s. And that's why this story matters now more than ever. Because somewhere, right now, there is another technology, working, proven, quietly solving a problem, and being ignored. This is the 6th turning point, and it leads to the question that actually matters. How do you spot it before everyone else? Here's the full system. You already have the first layer. Ask, what is separating the signals? Now add the second layer. What problem is being quietly solved that no one is talking about? And the third, what happens if this solution disappears? If the answer is everything breaks, you found something important. This is not theory. You can apply this today. Look at any new technology, AI devices, smart infrastructure, connected vehicles, wireless everything. Run it through the system. Most of it will fail, not because it's useless, but because it ignores the invisible layer. And a small percentage will stand out. Those are the ones built on real foundations. Those are the ones that last. Now let's close this properly. Final, write a number from 1 to 7 in the comments. Which turning point hit you the hardest? 1. The original invention. 2. The shift to silicon. 3. The underground survival. 4. The comeback. 5. The hidden billions. 6. The repeating mistake. 7. The future risk. Send this video to one person you know who keeps buying new tech but always complains that it doesn't work properly. One share could save them hundreds of dollars and a lot of frustration. And next week, I'm going to show you another system we almost got wrong, a power grid design from the 1930s, and an internal document that proves engineers already knew the flaw, but ignored it anyway. And the consequences are still affecting you today. Stay with me.